Yeah, he is on mute, I think, sir. You are on mute. Sir, kindly unmute yourself.
No, he is unmuted, ma'am.
Achha, he is unmuted.
Yeah.
Okay.
And we are live and ready to go. Yeah.
Yeah, so we have 1 minute's patience. I think so he's not able to hear us most probably. Otherwise, he would have responded.
I can hear you now.
You can hear us.
Can hear.
Okay.
Can.
Okay,
I
sir.
can hear you now. In between, I was not able to hear.
Welcome, sir. Welcome, sir.
Yes, sir. Sir, I'll just share my screen. Just give me 1 second.
What should I do? Should I start? Hello.
No,
can you hear me?
sir. Sir, give us 2 seconds. Give us 2 seconds.
Okay, yeah. Please let me know. That's it.
Yeah. Can you see my screen?
Yes,
Master?
yes. Yes,
Okay.
yes.
Yes, it's visible.
Okay. Yeah.
Yes.
So I once again extend a very warm welcome to Professor Vijay A. Singh, our next speaker. And he is going to talk about the golden ratio, the center of mass and aesthetics. It is an honor to introduce such a renowned physicist to the audience. So I would like to read out his introduction part. Professor Vijay A. Singh completed his doctoral degree from the State University of New York in 1978. He was a professor of physics at IIT Kanpur for over 20 years, from 1984 to 2004, and professor of physics at the Homi Bhabha Center for Science Education, PIFR, Mumbai, as well as adjunct professor in Center of Excellence for Basic Sciences, Mumbai University, and at IIT Bombay. He is a fellow of the National Academy of Sciences, visiting professor CEBS, and as well as the president of Indian Association of Physics Teachers. He was the National Coordinator Science Olympiads and the National Initiative on Undergraduate Science for 10 years. Under his mentorship, a large number of high school students have won gold medal in the Olympiads, and a large number of undergraduate students have carried out research projects, resulting in several international publications. Professor Singh has worked at several places abroad and has been a visiting faculty at universities in the USA. He has over 150 peer-reviewed international scientific publications. He was a co-author of the NCERT book, physics book for higher education for higher secondary school physics. He was also the chief editor of the Bulletin of Indian Association of Physics Teachers. One of his hobbies is to solve and design problems at school and undergraduate level physics. So thank you, sir, for sparing your precious time for our students and faculty members. And I have had a first-hand experience at his lecture, and he can correlate basic physics so beautifully. I'm sure we are all going to be benefited a lot from his talk. So thank you for sparing your time, sir. And over to you, sir. Kindly start your talk and share your screen.
So, Dr. Pushpa, I would like to mention that I had the pleasure of working with him a few years ago for an International Junior Science Olympiad. And it was amazing to listen to him, his ideas, and the way the experiments are dealt by with him, and the way the perspective of physics is totally altered, and is a very beautiful experience altogether. I can never forget those days. He remains a source of inspiration. And sir, we are just a few days ago, we had Professor Sharmishta Shahu with us, showing us experiments of IIPT, which he had designed and so on. So it's a wonderful thing. And we in the future also, we'll be continuing to have one IIPT expert person to speak to our students regarding the beautiful physics. Welcome, sir.
Welcome, sir.
Can you hear us?
Sir, can you hear us?
Hello.
Some network issue?
There is some network issue. Can you hear me? Thank you. Should I begin?
Yes, sir. Please.
Am I clear?
Yes, sir.
Yes, sir. But the screen is not shared and your video is kind of paused.
My window is paused. Should I?
Video.
I mean, I tried to sign in. What is the situation now? Can you hear me?
Yes, sir. We can hear you.
Hello.
I'm not able to see you, sir. We can hear you.
Yes, sir. We can hear you.
Okay. Okay, I think I'll need one feedback, say from Pushpa,
Yes,
Dr.
sir.
Pushpa
Yes, sir.
Binder.
Yes, sir. Don't
If
worry.
I'm not clear, please let me know. You
Sure,
have my
sir.
telephone number also.
Definitely, sir.
Okay, I'm happen to be abroad now, right now. So, but I've tried to make sure that I have a very good connection for this particular talk. I must begin by saying that I am very honored to be invited to give this talk. Thank you very much, Punita ji, for a very effusive addition to the introduction, which was also very effusive. Okay, I'm very sorry I missed the talks in the morning. I had every intention of doing it, but I was in some meetings. Okay, so basically, what I will be talking about is the golden ratio. I will share the screen with you in a minute, and it's basically some medieval mathematics. Okay, and in addition, there is some diversion into the Western concept of beauty and aesthetics and proportion.
Sir, we can't hear you anymore. It's paused the
And
video.
then, of course, it's all school level. Okay, say, why am I giving this talk? Okay, what are the unique selling point of this talk? And I would say the highest. This is the USP of this talk. I mean, you might say is that it lays the truth. 1 minute, there's somebody at the door. Please. It lays which should have been known 1,000 years ago. Okay, and which was discovered only, I would say,
I think, sir, there is some network and problem at
Yeah, I
place.
think the network
Sir, you can
is.
switch off your video and let only the audio on. Then the
around
bandwidth
5 years
will
ago
not be
by
loaded.
everybody should turn their video off
Yes, sir.
except
Yes, sir. We'll do that. We'll do
except
that.
mine because I have to speak. That's all.
Yes.
Yeah, kindly, because then we will lose out on this talk. It might get a little painful for both of us. So it was actually discovered 5 years ago. It should have been known 1,000 years ago, and then it was immediately accepted for publication in an international journal. So let me begin with this talk, and I've been always quite excited about this topic. So let me begin. I'll share my screen. I'll go to the application window. My screen should be somewhere. Where is it gone? Just give me 1 minute, okay? Just give me 1 minute, okay? Uh, I'll just minimize this for, just give me 1 minute, please, okay? Why is this not, okay. Now I will share my screen. Okay, here it is. So now, is my screen visible first?
Yes, sir. Yes, sir, it is.
Okay. Okay. So I've already told you what this talk is about. And this, what you see over here, physics.sutra@gmail.com is my email ID. Okay. So let me begin. Okay. I have to go down. Yeah, here it is. Thank you. Okay, so the talk basically has the golden ratio has an Indian origin. It was part of what is called a work of a 6th to 8th century AD mathematician Virahanka, okay, who said, let me think of the following series, he said. What is the series? It's a very simple series. He said you take 1 plus 1. I think if you can see my cursor, it should be here. You take 1 plus 1 and you add them together, you get 2. You take 2 plus 1, you get 3. You get 3 plus 2, you get 5. 5 plus 3 is 8. 8 plus 5 is 13, and so on. 21, and then you can go to 34, and so on. But that is the series. That is called the Virahanka series now. And if you now take the ratio of two successive numbers, 2 is to 1, you get 2, 3 is to 2, you get 1.5, 5 is to 3, you get 1.67, and so on and so forth. And the series then approaches an irrational number called the golden ratio nowadays. It is 1.618 dot, dot, dot. Okay. So that is what Virahanka did. Virahanka did something very interesting with it. He said something that we don't do nowadays. These are the days of plagiarism, right and left. He credited this to the fact that 1,000 years before him, Pingala, while studying Sanskrit meters and Sanskrit prosody, Sanskrit syllabic structure, he had actually designed a mathematical scheme which helped him arrive at the series. If you would like to know how to trace the path from Pingala 2,400 years ago to Virahanka 1,000 years ago or 1,500 years ago, there is an article that I will mention at the end of the talk. Okay. Before I continue, is my voice clear, Pushpaji?
Sir, yes, sir, it's clear. Yes, sir,
Okay, and
it's
you can
clear.
see the transparency, my
Yes,
slides.
yes, yes. Slides are also
Thank you
visible.
very much. Thank you. Thank you very much, because that gives me confidence that I can go on. So this was the series discovered by Virahank, and this was the golden ratio also hinted at by Virahank. Then what happened? Then what happened is the following. We have some interesting history now. Okay. History of mathematics, you might say. Indian mathematics traveled with the Indian spices along the spice silk route. Okay. So it traveled, and you can just imagine yourself, put yourself back 1,500 years ago. Just as the spices traveled, the mathematics also traveled on camels and caravans south of the Caspian Sea, north Persia, down to the Mediterranean, and then it entered Europe via Istanbul. And the first country it entered into was Italy. Not very surprising, Italy was the depositor. It got not only our spices, and you had a lot of rich merchants, including the Merchant of Venice, Shakespeare, but it also, the first universities were set up there. It was basically a transfer of knowledge from India and China to Europe. So similarly, our Virank series also traveled that way. It traveled from India to Italy. Okay. And there was one mathematician there who was very enamored of this, okay, who liked the series a great deal, and his name was Fibonacci. Okay. And I have not mentioned him here, but then he said I can generate the series also by another method, by a rule of rabbits, he said. Okay. Now Fibonacci was the Italian mathematician who liked this number. Okay, it's also, by the way, now known as the Fibonacci series. It should be, strictly speaking, the Virahanka series. He says, consider the rule. There is a mother rabbit which gives birth to one daughter rabbit every year. Okay. There is a daughter rabbit which grows up in 1 year to become a mother rabbit. And the third rule is that rabbits are immortal. Okay. With this rule, he said, I can generate Virahank's series. Okay. And how does he do it? Let me show it to you. First year, you have only the mother rabbit. Second year, you have the mother and her daughter. The third year, the mother gives birth to another daughter, but the daughter grows up to be a mother, so that is 3. The third year, the year after that, the mother gives birth to a daughter. You can see these two. The daughter grows up to become a mother, and this mother rabbit gives birth to another daughter. So again, you get 1 of 3 plus 3 and then 5 and then 8. And in this fashion, you have what is known as Fibonacci rabbits. And you get the golden ratio. So that's the golden ratio. It's an interesting series. I have to tell you something about Fibonacci. Fibonacci not only got this number popularized in the West, okay, but he did something interesting. He got the European mathematicians to accept the number 0. Prior to that, the number 0 or nothingness was banished because it was the sign of the devil. There is no such place as 0. There is always God there, they said. Okay. What Fibonacci convinced them, the mathematicians, that forget about doing mathematics. You can't even do trade with the Arabs and the Indians if you don't accept the number 0. So let me continue with my story. The story goes on, and there are other representations of this number now. It is basically the solution to the quadratic equation, x squared minus x minus 1 equal to 0. Okay. So you basically, when you solve this, we all know the solution at 9th standard level, 1 plus root 5 by 2, you get the Fibonacci number, or you get the golden ratio, 1.618. Why golden? We'll come to it in a minute. Okay. The other solution to it is minus 0.618. And very interestingly, if you multiply these two solutions, you get minus 1. Okay. So that's another mathematical representation. But there's an even more interesting one inspired by Ramanujam, okay, in terms of continued fractions. What Ramanujam would say is that you take x equal to 1 plus 1 and you divide it infinitely continued fraction wise all the way down. And since, as we have a Sanskrit saying, Om Purnamada Purnamidam, the infinite is contained in the infinite, in the denominator over here, which I'm now circling here, let me highlight this. In this denominator over here, you replace it by x. And if you replace the entire denominator by x, you'll get this quadratic equation x square minus x minus 1. So about Ramanujam, it is said that every number was a friend of Ramanujam, or vice versa. Ramanujam was a friend to every number. Every number he had something special to say. So what I hope that is by the end of this talk, you will become friends with at least one number, and that is the golden ratio. 1.618 dot 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 dot. Okay, so that is about some medieval mathematics. Let us continue. Okay, what is got this? Why is this called golden? What is this got to do with ratio? It is basically a question of proportion. Okay, so you have to see the slide in a somewhat convoluted way. If you look at the top left, this is the Parthenon in Greece. Okay, near Athens. Okay, what they say is that if you look at the breadth, okay, and you look at this height, and you divide the breadth by this height, you will get the golden ratio. It's like 1.62. Leonardo da Vinci, the great Renaissance person, was also very enamored with this ratio, golden ratio. Okay, he said that if you look at Mona Lisa's painting, let's say the distance between the two ears, okay, you put it in the denominator, the distance from the height to the chin, you put it in the numerator, and that ratio is also 1.62. It's a perfectly proportioned figure and face. Okay. Not only that, he drew what is called, and which is probably not very clear in the slide, something called the perfect man. It's called a Vitruvian man. It is based on an idea due to Vitruvius. What Vitruvius said is that any structure, including a human structure, should have three things. It should have strength, it should have functionality, okay, and it should have beauty and proportion. And he said the proportion should be in the ratio of the golden ratio. For example, if you stretch your arms wide, and if you look at the height divided by the distance between the stretched arms should be 1.618 or 1.62. Once this was discovered and this was made popular, okay, and by the way, it has been made very popular by Dan Brown in his book, in all the series of books that he has brought out, okay, the golden ratio phi, as he calls it. Indians also discovered it. For example, people say that the entrance to the Taj Mahal is as per the golden ratio, okay. But then I found something interesting about 7 years ago when I was traveling near my village. I went to a wedding place, and particularly among the folks in Bihar, that wedding room, so to say, where the bridegroom and the bride have to spend a few nights and a few days together. Okay, the wedding room has a wall which is painted, and on that painting I saw a painting which you are seeing, which I have now, which my cursor is at right now. There was a big circle, and inside that there was a dark circle. So taking a scale from the local schoolboy in that house, I measured the ratio, and the ratio turned out to be 1.6. Okay. So this turns out quite interestingly. I thought it was the golden ratio. At that time, Dan Brown had made the golden ratio very popular again. Okay. And if you look at for example, this painting of Shiva, and if you look at the moon is as per the golden ratio. Okay. Let us continue with the element of beauty for the moment. Okay. What I'm trying to say is, according to Leonardo and many other architects, the best proportion is one which is 1:1.618. Okay. If you have something like this, it looks very thin. If you have something like this, it doesn't look good, but this proportion looks proper according to them. Okay, so which rectangle do you like the best? I want the universal answer, like the middle one. Okay, but there is something else. The story doesn't end. The mathematical story continues, and I will come back to the mathematics in the end. But let me alert you to something right now. Okay, I will first look at the square. There's a square with unit size 1, another square next to it with unit size 1, and then there's a bigger square which is 1 plus 1, which is 2. And then 2 plus 1 is 3, a third square, 3 plus 2, 5, a fourth square, and 5 plus 3, there's another square, which is 8. Okay, right? So you have this. Now you do one thing very interesting. You start from one vertex of the smallest square, and you draw a curve which is a tangent to it, making sure that it hits the boundary between the two squares 1 and 1 as a tangent, and the boundary between 1 and 2 as a tangent, as you can see, the boundary between 2 and 3 as a tangent, 3 to 5 as a tangent, and 5 to 8 as a tangent. Okay, so you draw this curve, which is a spiral. It is called a golden spiral. Okay, it is a curve which is also known as the Fibonacci spiral, and it was made very popular by a later mathematician, Bernoulli, who was very enamored of it. Okay, and he liked this curve a lot, so that he has got this curve plotted and sort of engraved on his grave, actually. Okay, so there's one thing very special about this curve, which I should just point out to you, and that is if you go to the center of the square of the spiral, sorry, not the square, of the spiral, and you draw any line to the curve, okay, and at this point you draw a tangent. The angle made by a tangent at any point and the line joining that tangent point to the center of the spiral will always remain constant, will make a constant angle. For example, if I draw a tangent at this point, you can see it, you may not see it, but let me draw my cursor like this, and you draw this point and connect it to the center of the spiral. Say the angle is 60 degrees. If you take any other point, draw the tangent at this point, and then join that tangent point to the center, that angle will also be 60 degrees. Okay. So what it means essentially is that as you go around this curve, you must make only a constant angle of 60 degrees to watch the center of the spiral. Okay. Now, this golden spiral is there. People, as it is, people discover things which are not there. You try to see things which are not there. So people started saying golden spiral is everywhere. Okay. Whether you look at a conch shell, you look at a rose flower, you look at the sunflower, or you look at the spiral galaxy, you will see golden spirals. Not so, I would say. But anyway, you can imagine that this is very popular and this is true. So let us say the golden spiral is everywhere. Okay. Right. Okay. Then the question arises is, you have told me the following. You have told me the mathematics. Then you have told me why the golden ratio is so popular in Western aesthetics and sense of proportion. What about physics? Okay. So before I launch into the physics part, I'm still in the first, I would say, trimester of this talk, so to say, first 1/3 of the talk. If you go to the physics part, but let me pause for a minute. Is my voice audible and clear?
Yes, sir.
Yes, sir.
It's
Yes, sir.
clear.
Yes, sir.
Thank you very much.
Yes, sir.
Thank you very much. So I would like, okay, so let me show you one and then I'll go back to the previous one. In physics, for example, you see these problems. For example, there's a problem in the European Journal of Physics in which you have infinite capacitors, okay, equal capacitors, but they go on infinitely. And you say, what is going to be the effective capacitance of this network of capacitors? If you work this out, it turns out that it's going to be C0 into the golden ratio, 1.618, okay. Additionally, and how does it happen? I'll tell you how it happens, okay. And that's why I have to go back now and show you this curve. You take infinite series of resistors, okay. Take the infinite series of resistors and you say, what is the effective resistors between these 2 points? I have not shown you that infinite series, by the way. That's why I showed you the infinite capacitors, to get you an idea, get you a feeling for what I mean. What you do is you truncate that series and you replace this infinite series by itself. The same idea as how the infinite is contained in the infinite, part of what is there in the Upanishads, Om Purnamada Purnamidam Purnata Purnamudachyate. Okay. You put that in here, okay. And now you say, what is going to be the resistor, effective resistor here? It is very simple. This is equal to R, okay. I've got an R over here, plus these two are in parallel to each other. So you'll get R equivalent into R divided by R plus R equivalent. It's written right here. Okay. And if you simplify this, you'll get a quadratic equation. Okay. So what I'm saying is that if you do this, if fit resistor network properly, you will get a quadratic equation of this type. And if you divide this entire quadratic equation by r square. Okay, that is, you say x is equal to r equivalent by r, I get the same equation which leads to the golden ratio. So the answer is the equivalent resistance is equal to r into the golden ratio. Okay, so that's where you see it. It's a work by T.P. Srinivasan in the American Journal of Physics long ago, 1992. It's also an IIT problem, by the way. It has come in IIT already. Okay, and it is basically uses this idea that the infinite is contained in the infinite. So in capacitance, you see it. Then there are some scattered problems then which you can see. There are one-dimensional toy models where you can see it. Okay, okay, but these are all scattered occurrences. Okay, this golden ratio phi is the golden ratio phi. I'm getting a disturbance here. Saroj, please.
Please mute yourself.
I'm so sorry. No, there's a kid who is disturbing me. Okay, happens to be my grandson who doesn't realize that I'm giving a very important talk.
Sorry, I thought some
No.
participants.
He barged in. I don't know.
Really sorry, sir.
No, I'm sorry. Because anyway, that was a good diversion. It is not like pi or e. You know, when you look at pi, it is such an important irrational number. Okay, that it occurs everywhere. Time period of a pendulum. If you have Kepler's third law, t square proportional to r cube, again there it appears pi will come. If you look at, for example, the Bohr quantization rule, the Bohr-Sommerfeld quantization conditions, h by 2 pi, this pi is everywhere. It is ubiquitous. So is E, the base of the Naperian log. You look at the growth of bacteria, you look at the decay, nuclear decay, you'll find the C. The golden ratio is not like this. Okay, it comes in scattered ways, it will come, it will not come. So what I'm going to tell you now, okay, in the next 20 minutes or 30 minutes, and I've already, I think it's been about some time now, what I will tell you is basically that we have found a universal occurrence of the golden ratio in physics. Okay, that's the lesson. Okay, so let's continue. So we go to the third theme of the talk. I've told you a little bit about the mathematics. I've told you about beauty. I've told you how golden ratio is never found anywhere in physics or very rarely found. It is not as popular as Dan Brown would like you to believe. Okay. By the way, I will tell you a bit more about this Dan Brown later on. Okay. We come to the center of mass, the third theme. That is how I tie it together. You can find the center of mass in a number of ways. Okay, the simplest way is what you see on the right-hand side. It's called the knife edge method. Find the point at which you can separate, at which you can support a laminar body, and that is the golden ratio. You have a pen. I think you're all carrying a pen, and if there's a desk, you want to know what is the center of mass of your pen. All that you'll do is you put the pen on the table and you will slide it perpendicularly along the edge of the table and see where it falls. And that is the point of the center of mass. Okay? So that is how it is found. Center of mass, I have to tell you, is like a very important concept in physics. Okay, and we all know about it. I mean, and it's also very useful in life. For example, if you look at this, the center of mass of the human body, here is the knife edge method. There's a yogasana which tells you what is the center of mass of the human body. It is very close to the navel. This person at the beach is doing Mayurasana. The center of mass was used in a very, very intelligent way and a wonderful way by a person who did revolutionized high jump. Okay. It's called the Fosbury flop. Prior to Fosbury 1966, 68, I think, 68 Olympics, everybody would jump a high jump bar in the forward direction, like a horse jumping over. What Fosbury did was he jumped backwards. Okay. And he created a sensation because he could jump at least half a feet higher. What he is doing essentially, as you can see in this figure, is he's keeping the center of mass as low as possible. Okay. Half his body is below the bar, half his body is above the bar. His center of mass is just above the bar, and he has cleared it. If you jump in the forward direction, your center of mass is at least a foot above the bar, if not the entire 2 feet above the bar. Okay. And this is called the Fosbury flop. There is a physicist. He's done his BSc in physics. He's the greatest hurdlist of all times. His name is Edwin Moses. He did the same thing. He calculated the distance between two hurdles, measured his steps in such a way, and he ran in such a way that he always kept his center of mass as low as possible as he's jumping over. Okay, he's won the largest number of gold medals as far as the hurdles go, and he's Edwin Moses, a BSc in physics. So he's used this physics to advantage. Okay. After he did it, you can see everybody and his brother and sister started jumping in the same way. Okay, this jump, jump, jump all the time. The center of mass is intuitively obvious to this kid on the beach as he's balancing himself or herself. I don't know if it's a boy or a girl. Okay, and this is here what he follows the Bombay Darshan bus. A wrong use of the center of mass. All the kids are on top. I mean, the bus is top heavy. It's about to fall. If you ever go to Bombay, don't board this bus because it's likely to fall, and don't go near it because it might fall on you. Okay. So it's a very useful concept. It has been used also in what is called the wobble method. Let me not, this is too elementary. It is a very heavy boy. There's a lighter girl. The heavier boy has to be close to the center of mass to balance this plank. Used where? Used in actually finding out extrasolar planets. Because you have the planet and you have the sun or the star and you are watching it. What happens as the planet goes around? Okay, the star wobbles, it goes back and forth so that the center of mass is, which is shown by a red cross, is fixed. So the star is going, the planet is going around, the star is wobbling. You never see the planet. When you see extrasolar planets by a telescope, or the Kepler telescope or whatever, you never see the planet, you see this wobbling. And you never see the wobbling, you see the Doppler shift. Okay, but the concept is very simple. The concept is the center of mass and the invariance of the center of mass as two bodies move. So the idea is all these things are important. Okay, the maths is important. There's a golden ratio, 1. Okay, and what is also important, can you also see me or you cannot see me? Should I, is my camera off or something?
Sir, your camera,
Sir,
sir, you
camera
are
is
not
off.
visible.
No, you are not
but,
visible.
but your presentation is visible.
Good, as long as it is, the face is not important. Okay, but sometimes the gestures are important. Okay, so this is the one thing I don't like about online. Okay, because I can always never get the technology right, I find. Anyway, so you have the golden ratio, mathematics, you have some talk on diversion on beauty, and you are now told about the center of mass. So now let me put it all together, okay, in the next 15 minutes and tell you the story, okay. Oh, by the way, there's more on the center of mass. I mean, the center of mass, by the way, leads to bilateral symmetry on Earth. If you have one wing on this side, you have another wing on the other side. This leaf has to have bilateral symmetry because if one side is heavier, it will sag. So if you have one hand, you have another hand. If you have one leg, you have another leg. You have to be symmetric. You must have bilateral symmetry demanded by keeping the center of mass at the center. Okay. Same thing with this beautiful peacock. Okay, it has to keep the center of mass at the center. Same thing with the ballet dancer. She may be dancing and she looks very pretty as she dances. Okay, but the center of mass is right here at the foot. It goes straight through. So the center of mass is also, as I said, not just a useful concept, it's a beautiful concept. Okay. So just as Vitruvius said that any structure must have strength, functionality, and beauty, center of mass has not only importance of its own, but it is also beautiful. Okay. So now how do you calculate the center of mass? Actually quite simple. Okay. All that you do is you sit over here. If this is the origin, you just take m1 into whatever the distance is, in this case, the 2 kg mass is at 1 meter. If the 4 kg mass is at 4 meters, then you divide it by the two masses, you'll get 3. Okay. I'll pause at this to tell you that there is another way to find the center of mass, which all students at 11th and 12th level should know, or probably do know. Okay, and that is the following. You sit at the center of mass and call it the origin. Okay, and you know the distance between the two masses. It is 3, 4, and this is 1. 4 minus 1 is 3. You sit over here. And you say, okay, let this distance be x. I don't know what it is, but let it be x. I know the total distance, but I don't know where my center of mass is. I sit here, I do 1 x into 4. 4 into x is equal to 2 into 3 minus x. And if you solve this equation, again, you will get x is equal to 1 centimeter or 1 meter, which means this is 1 meter from here. Okay. So the second way of doing it tells you don't have to do any denominator calculations at all. You just sit at the center of mass, set xcm equal to 0, and just do 4 into x is equal to or minus 2 into 3 minus x is equal to 0. Okay. So that's the faster way of doing the center of mass calculation. Okay, so now our story begins. Okay, and let me start with it. The story actually began in 2014. Some of you are familiar with the Kishore Vaigyanik Protsahan Yojana. Okay, it's a very important scholarship exam of the government of India. Okay, and at least 1 or 2 lakh students sit in it now. Okay, this was 2014. This was a question that Dr. Praveen Pathak and I had set. We asked the very simple question that here you have a square. The square has a side A, therefore it has an area A square, and therefore its diagonal is square root of 2A. I remove a smaller square from here. From the vertex, I cut another smaller square, and I ask the following question. How much of the square should I cut so that the center of mass will be at the edge G? Okay. If I cut only a very little amount of the square, a smaller square here, then the center of mass is well within the bigger square. If I cut more, then center of mass is outside it. Okay. But if I cut just the right amount, I will hit a golden point, and that point is the center of mass is right at G. Okay. And what should this ratio A by B should be so that I get it right there? Okay. So now I think you know the answer. It will turn out to be the golden ratio. Okay. But let me go through it a little bit. Okay. This is the same problem, the same thing. And here is the calculation. Okay. In this calculation, all that I will request you to do, I will go over this calculation twice for you, and then I won't go over the more complicated calculations. But I think I should do this at least so that you will know how to do it tonight if you're at home and you want to amuse yourself. Okay. You look at the mass of the square, the total square. The mass of the total square is m0. That I write as rho into a square. Rho is just the surface density or the superficial density of this laminar body, the square. Okay. You look at x0. X0 is the position of the center of mass. Okay. And if you're sitting here at the so-called mythical center of mass, okay, this x0 is nothing but GB minus GO. That is what is written here. GB minus OB, sorry. Okay. GB minus OB because the center of mass is just GO. Okay. Right. So what is GB? Not difficult. GB is just root 2 into B. So I'll go down here. GB is equal to root 2 into B. And what is OB? OB is this thing. I just point out. This is OB is equal to root 2A divided by 2. So it's A by root 2. Okay. Minus, because I'm subtracting and cutting this out, minus the mass of the smaller lamina, which is rho into B square. Okay. That is the rho. What is rho? Rho is the density, superficial density, and B square is the area of this so-called lamina that I've cut out into G times O prime. Okay, now what is G times O prime? It will be B by root 2. Why is it B by root 2? Because it's root 2B divided by 2. Okay, so B by root 2. So what you get, if you set the numerator to 0, forget the denominator. You set the numerator to 0, you get a cubic equation. Okay. That cubic equation can be factored. One factor is x minus 1, and the other factor is x squared minus x minus 1. By the way, what is x? X is this ratio A by B that was asked in this problem. Okay, right? And the solution, as you can see, this equation is nothing but the golden ratio. You might say, what about the other solution, sir? What about x minus 1? That is the solution x equal to 1, which means A is equal to B, which means you must cut out almost the entire square and you're left with a line like this and a line like this. Naturally, if you have two lines, A into this and this one, then the center of mass is right here. So the other solution has a meaning, but it is the trivial solution. It is this solution that I'm after, and it turns out to be the golden ratio. Okay. Any questions? Well, let me show you something else. And if there's still a question on this algebra, I'll tell you. So that reminded me of that circle I had seen in a village in Bihar, that wedding room, picture on the wall. They actually paint it on the wall. These women are actually village women who painted on the wall with vegetable colors. Okay, they don't even use these so-called newfangled colors, chemical colors. They do it with vegetable colors. It's called Cobra painting, by the way, if you're interested. Okay. So here is the picture, and I want to draw your attention to it. Okay. I've cut out a circle inside a circle, and I want the center of mass to be right at this point. Okay. How do I do this calculation? I know that the area of the circle is pi into r square, which I've written here. I forget that pi, okay, and I multiplied by this surface charge surface mass, which would have been sigma or rho, so that also I forget. So the pi cancels out, the rho cancels out. I have an r square. From here, the center of mass is at this point O. What is this point O? This point O is this entire 2r, small r, I mean, divided by the entire 2r divided minus small 2r minus r. So 2 times small r minus r is what I'm getting here. What about the smaller circle? The smaller circle has a mass which is pi r square sigma. Forget pi and sigma. And then I have the distance GO prime, which is small r. If I set the numerator to 0, divide r by r, lo and behold, I'll get the solution, which is the golden ratio. Now, what does this mean? Okay, if you have not followed the algebra, you can stop me now, or you can work it out at home. I'm saying, and there's such a simple thing that you can always work or both these things out at home. Okay, remember the square root of 2 is almost like sine of 45 degrees. Okay, it is for sine of 45 degrees. Okay, so turns out there are 2 occurrences of the golden ratio that we found. But since it is true for a circle and it is true for a square, we thought, why not investigate all kinds of polygons? Okay, so we took every even-sided regular polygon, every one of them, and every one of them has this property. But I'm getting ahead of my story. That is the universality. What it means physically is that if I've cut this out in the proper, perfect proportion, in the golden proportion, then I can balance my disk on this point G. And that is what you see over here. That's a picture of me. I've actually had a kid cutting this out for me, and I'm balancing it on my knife edge, which is my forefinger. Okay, so you can actually balance it like this. That is what it means. Okay? Now, the point is, here is my square, and I go ahead and I look at this. I can make 2 kinds of excisions. The excision that we had asked in the KVPY problem was the vertex excision. Okay? But I can also make a midpoint excision. Okay? And if I make a midpoint excision again with A by B equal to the golden ratio, this point G is the point where the center of mass will reside. It will not reside inside. It will not reside outside. If I cut less of it, the center of mass will be in the body of the lamina. If I cut more of it, the center of mass will be outside the body. But there is one golden point at which the center of mass will be right on the body. Okay. So there are 2 ways of doing it, and both ways give me this. In fact, we were so amazed as we went along that when we looked at every even-sided polygon, okay, like I will not show you this calculation. Don't worry about this calculation. Even for this even-sided polygon with the vertex excision, okay, regular polygon, of course, if you look at the longer side divided by the smaller side, okay, it has to be the golden ratio for perfect balance at the point G. For perfect balance at the edge point, remember the edge point, okay, that is for the vertex excision. If I do a mid-size excision, that is to say, if I don't cut it from here, but I cut it right in the middle here, okay, as I'm doing in this particular diagram, once again, unless A by B is equal to the golden ratio, the center of mass will not be at this point or the edge point. So now what do? This is what I meant by universality. Okay, to look at any laminar body which is regular, Okay, there is a universal property, and that is it can be balanced at the edge provided you have the golden ratio. So I've given physics importance, a universal importance to the golden ratio in physics. Okay, and that is this particular one. It's a simple thing. It should have been known to every person after 1,000 years ago. Okay, once the center of mass was discovered, say at least after 1676, when the Principia was written. Okay, it should have been obvious, but it was not. Okay. Then we look at biscalar body. Look at a rectangle. Cut out a smaller rectangle. Okay. If B by B prime is equal to the golden ratio, A by A prime is equal to the golden ratio. Once again, the center of mass will be at the edge G. Okay. Whether you make a vertex excision that I had done earlier in this particular figure, or you make a mid-size excision over here, once again, it is the golden ratio. Not only that, you look at a rhombus, same thing, or you look at an ellipse. All this we mentioned in the paper that we published in 2016. Okay, but that was not enough. That is not the only thing which I think excited the editor of that journal, which is the European Journal of Physics. Okay, now what excited him more, I think even more, was the fact that if you go to three-dimensional bodies, okay, now I want a three-dimensional body in which I remove a small square cube out of a larger cube. Once again, if A and B are in the perfect, are in a certain ratio, okay, I'll tell you what that ratio is in a minute. Okay, you can balance, the center of mass will be at the edge. Okay. Same thing is true of a sphere. Now, what is that ratio? That ratio is basically not the solution to this quadratic equation, x squared minus x minus 1. It is the solution to this cubic equation, which looks very much like this. X cubed minus x squared minus x minus 1 equal to 0, which has a real solution, which is 1.8. If the ratio of A to B is 1.8, lo and behold, the center of mass will be at the edge. You look at the tesseract. Now, where have we heard of the tesseract? In the movie Interstellar, which some of you must have seen. Once again, the tesseract will be balanced at the edge, provided you are at the solution of x4 minus x cubed minus x squared minus x minus 1 equal to 0. There's the four-dimensional body. What is the solution of this? The solution is not 1.83, the solution is not 1.62 or something, 618. It turns out to be 1.92. Now you get the idea. If you have a large dimensional body, you will get an equation which will be like xn minus 1, and so on and so forth. The real solution to this, the one which is the fractional, or what you say, the irrational root, goes from 1.62 to 1.8 to 1.92, and it inches towards the number 2. That is also not hard to figure out. For example, if I put x equal to 2 here, this is 16, and the rest of it is 15. 16 minus 15 is 1. If I put x equal to 2 over here, no, sorry, this is 8. 8 minus 7. This would, if I put x equal to 2 over here, I'll get 16. 16 minus 15 is equal to, you'll be left with 1. So you're actually inching towards this number 2. But what was interesting to us mathematically, so now we are back to mathematics again, okay, is that these complex roots have a very interesting structure, we found. Okay, and let me show it to you in the next figure. What I've plotted in this figure is the real part of x and the imaginary part of x. Okay, all the roots. And as you can see, say for a 16-dimensional body, these roots are all lying on a circle. And if you go to higher and higher things like 512, they make a very dense circle. Okay. So we are still exploring some mathematical properties of this golden ratio, of this equation. So now we have gone back to mathematics to explore why, what an interesting equation this is, whose real root, it has one real irrational root inching towards 2, and the other one is lying on a circle. Okay. So that is the point. So I've told you some physics, and I've told you some mathematics. Okay. So let me make some, how should I put it? Let me make some concluding remarks. But let me wait for a minute. I've finished 46, I think 46 minutes. Are there any urgent, any questions you have at this point about any of this?
No, sir, no questions till now.
Not yet.
So again, as Dr. Anurag Sharma said it, it's either entirely transparent or entirely reflecting, but I'm hoping it was entirely absorbing.
Yes,
Okay.
sir. Yes, sir.
Yeah.
Definitely.
That is what we all hope for. So here I'm coming back to the, I'm coming back to the spiral again. Okay, these are three or four concluding remarks, and bear with me while I conclude my talk. Okay, the spiral, as I said, was a favorite of Jacob Bernoulli, 1654 to 1705. It was so popular. It was so in love with the spiral, golden spiral, that he had it inscribed on his grave. Okay, and I found something very interesting, okay, which I thought I should share. You can see this bird. This bird is approaching a prey. Okay, this bird is called the falcon. Okay, the falcon is approaching the prey, and the way the falcon approaches the prey is very interesting. It moves at breakneck speed. It's almost 100 meters per second or even more. But it goes around in a spiral and then it approaches us. Okay, as it goes around in a spiral, okay, this prey is confused. He always thinks that this falcon is going somewhere else. He looks at the tangent of the curve. Okay, so he's at peace because he thinks this falcon is not coming at him. Okay, it's called the Shaheen, by the way. In Urdu, it's called the Shaheen falcon. Okay, and but what is the falcon doing? Why is he choosing the golden spiral? He chooses the golden spiral. And by the way, if you might know, if I'm pulling a fast one on you, this is in the Journal of Experimental Biology 2001-2002. That it's a golden spiral. And I think it is the golden spiral.
Sir, you are not audible.
Yes, sir, not audible.
Sir, voice is breaking.
Now,
Network issue, I think.
Network issue is there, I think.
now I'm audible. Hello.
Yeah.
Yes, sir, but
Yes,
your
sir.
I'll just
voice is
pause.
breaking.
I'll just pause for a minute. When did it start breaking? All along?
No,
Just
no,
now,
no,
just
no.
now,
Just now. Just
just
now.
now.
I don't know why it broke, but
Now
Now
it's
it's
now
clear,
is
sir.
it
fine.
clear?
Yeah. Yes, sir.
Okay.
Fine. Fine.
My microphone was away from me. Okay. So I'm holding it close. So by the falcon, okay, I'm talking about the falcon. How much of the falcon did you hear, the story of the falcon?
Just that the prey doesn't know that the bird is coming at him.
Yeah,
He's
that
going
the
to kill the
falcon.
squirrel.
Yeah, because he's going around in a circle. But the falcon is using a golden spiral.
Yeah.
And this, by the way, is in the Journal of Experimental Biology 2001 or 2. If you're interested, I'll send you the paper. I think the falcon does it because he's making a constant angle with the prey. Okay. Remember I told you that this angle made by the tangent to the curve with the center is always a constant for a golden spiral, like 60 degrees. He's going around at very high speed. If he has to keep turning his head right and left, he'll feel dizzy, or she will feel dizzy. Okay, it's usually the female which hunts, by the way. I have to tell you another interesting story about birds, and that is that the female of the species is larger and heavier than the male, for raptors at least. For raptors. Okay. Anyway, so that is what it does. And that sort of reminded me of a very famous line. I don't know how many of you are fond of Urdu poetry, but I would like to recite it here. Okay, as the finale of this very interesting session, which I have missed since morning. It is by Faiz Ahmad Faiz, the great Urdu poet. He's from Pakistan. It's by, I think this is by Iqbal. This is not by Faiz Ahmad Faiz. This is by Iqbal on the Shaheen. Japatna Palatna. I mean, Iqbal knew how the falcon is approaching before the Journal of Experimental Biology. He said, Japatna Palatna, Palatkar Japatna. Lahu garam rakhne ka hai ye bahana. परिंदों की दुनिया का दरवेश हूं मैं ये शाहीन बनाता नहीं आशियाना to swing, to swerve, to swing back again. Okay, this is not for the prey. That is what Iqbal says. The Shaheen is doing it to keep the blood roiling in his veins. I am the Sufi dervish of the bird universe, of the avian universe. Okay, that's what he says. It's a wonderful poem by Iqbal. and you might want to read the whole poem at some point. Okay. So not only I would say Bernoulli, but even Iqbal was enamored of this golden spiral. Okay. There's another thing which I wanted to tell you as a concluding remark. There are other centers in physics. Okay. One is the center of buoyancy. Okay. Is a part of the body that is submerged in the water. That part ka center of mass is not the same as the center of gravity. Okay, that's called the center of buoyancy, the point at which there's an upward force on the body. And they don't always match, therefore the bodies can tend to tilt. There's another one called the center of percussion. Every cricketer or every person who's held a bat knows about it. If the hard ball, I would say the season ball as we used to call it, hits a particular point on the bat, it goes straight to the boundary and your wrist does not even feel it. The reaction is zero. A standard problem in joint entrance exam. A third one is the center of pressure, which you may have not heard about. Okay, the center of gravity is one thing, but the Bernoulli's principle, which pushes it up, might not coincide with the center of gravity. Therefore, the plane is flying in an unstable mode. In fact, most fighter planes have their center of pressure, by the way, outside the body, outside the main body, and they are always in the unstable mode. Okay, so there are other centers of mass. The center also plays a very important role. The word center, by the way, plays an important role in, how would I say, poetry. There's a poem by Yeats. Things fall apart, the center cannot hold. Here is a long quote by Black Elk, the famous last Native American Indian as we are calling it, Red Indians as we are called, last quote, before about 200 of them were massacred at a place called Wounded Knee. Okay, there's a very famous book by that name. Look at what he says. When you talk about things, you talk about the center. Okay, the nation's hoop is broken and scattered. There is no center any longer, and the sacred tree is dead. So the word center is important in literature. The word center is important to express an important thought. Okay, okay, and this is the summary of the talk. Two-dimensional structures have been around since time immemorial. So has the golden ratio. So is the notion of center of mass. But it is surprising that nobody seems to have noticed this connection. Okay. The center, by the way, phi has been made very popular by Dan Brown. And if you just go and Google, say for example, for perfect beauty or something like that, the Blue Bella, the famous fashion giant, has declared that Scarlett Johansson is the most beautiful woman in the world based on the center of mass, most well proportioned, based on this golden ratio. Okay, so everybody is also making money out of this golden ratio. Okay. We have found systematic repeated occurrences of this, and we have endowed it with a physics-based meaning, and we have generalized it to higher dimensions. These are the three takeaways from this talk. Okay. If there are students at 10th or 12th who would like to do some small research problems, there are some that I have in mind. Okay, and here is the reference. The original reference is by Praveen. The work is by Praveen Pathak and myself in 2016 in the European Journal of Physics. It was followed up 2 years later by a follow-up publication, again by Praveen Pathak and two people from Ahmedabad, Gautam Datta and Mitakshi Mehta. They are both lecturers. I think Mitakshi is a lecturer at a college, and Gautam Datta teaches in an engineering college. Okay. And if you are very interested on how Virahanka arrived at his series based on Pingala's work on Sanskrit prosody, there is an article just last year that I thought I should write along with a girl student, Nivedita, in the bulletin of the IIPT, March 2020. Okay. So that's the talk. Thank you very much.
Thank you so much, sir. It was an outstanding and amazing talk. It was really very good. It was a visual treat, I must say. All those beautiful pictures, so many examples of golden ratio in physics, in paintings, in structures. It was too good. Even the pictures that you shown for center of mass, they are amazing. So So beautifully, everything you connected so well. So thank you so much, sir. It was indeed a very, very interesting talk, I must say. And the pictures and your piece of research work is also very, very, inspiring that people could think of like problems like this and they do come up with such results. So thank you so much, sir. It was as good as possible. So we are indeed indebted to you for sparing your precious time for this talk for the students and for the faculty as well. So thank you.
Thank you very much. Okay.
Yeah.
Thank you
So
so much,
now there's
sir.
a
Thank you so much,
career
sir. I
center.
must say, sir, that I always say that I'm greedy for more knowledge, and I would like to tell the audience his lecture on Bombay and physics, which I heard in 2019 in Allahabad, along with his
Mhm.
coffee table book on Bombay and physics, is mesmerizing too. So, sir, we hope to have you with us again with another another set of lectures, which are always as interesting as ever. So I
Thank
think
you.
everybody agrees with me that his lectures are intoxicating, intriguing, mind-opening, and changes your perspective completely. Thank you so much, sir, for being a source of
Thank you.
inspiration.
Thank
Yes,
you.
sir. I
Thank
also agree to it, Punita and Dr. Bindal. I think we should plan more lectures. We should plan more lectures in our college for sir.
you. Okay.
Thank you so much, sir.
Yeah. Yeah.
Yeah, thank you.
Yes.
And thank you
Thank you,
for
sir.
these nice comments. It encourages me to make similar talks and do similar research work with high school and higher secondary school students.
Definitely,
Sir,
sir. They are
also
Yes,
with
very
sir.
college
good.
students. Sir,
And
please,
undergraduate, first
sir,
year
please,
undergraduate. First year.
undergraduate students also.
That is what I've done,
They're
by the
also
way.
small.
Yeah.
Yeah. With
Even
basically,
even
so far I worked with first year and second year undergraduate students. There have been only very few at the school and higher secondary school level. Okay. So anyway, yeah. First year
Our
is they are
students would
mature enough
also
at
be
that point to
happy.
do it.
Our students
Yes.
will also be happy to work with you under your guidance, sir. That would
Yes,
be
sir.
extremely nice for them.
Yes,
Thank
yes,
yes,
you.
sir.
definitely.
So,
Definitely.
so they make a
Definitely.
small contribution to the general body of human knowledge, and that is good for them, good
Yeah.
for us.
Yeah,
Yes, sir.
yeah, sir.
Yes.
Sir, it's a service to the education. How will they, get to connect with physicists like you? I mean, this is really good.
Thank you very much. Okay.
Yeah.
Now we go to the closing ceremony.
Yeah,
I will.
yeah, yes, sir. So I think we have come to the end of the online national seminar. So I would like to basically close with the valedictory note. So I start
Dr.
formally.
Bindal,
Yes,
Dr. Bindal, do you allow me to show something very nice
Yes.
made done by students?
sure, sure. Why not?
Yeah, sure. Yes, please.
So I would just like to, if the screen is stopped from sharing, then probably I
I think
can.
it stopped from sharing. Yeah. Why is that? Yeah. Why is this?
Sir, down
I'll
or up?
stop sharing.
Either, yeah,
Oh,
it's
should I
stopped.
stop sharing my screen? Just
No, no,
stop
no,
me
sir, it's
somehow.
okay. No, it's
Okay.
okay, sir. We can see you and
Okay.
your screen is stopped from sharing. So
Okay.
that's
Good.
not a
Thank you.
problem. So, sir,
Thank you.
with your nice presence in our department today and it's a webinar, I present to the people who have gathered here, the teachers, the faculty, and the students, the magazine made entirely by our students. Here you can see it, Microcosm,
Yes.
exploring the universe. This magazine has been
Oh,
compiled by the students of BSc Physics Honors and BSc Physical Sciences. They have made their own group and they have done their own research and they have tried to come up with a magazine. This was also in force earlier, but now it will be there for every month. And they have had several components in it. And here is also Indian heritage. So there is a section of Indian heritage. There is a section of career counseling. There is news flash. There is a, so I shall just go to the next page. And as you can see, they have found out who are the people who have done different types of things. There is a detail about our senior most teacher, how she joined, and that's inspirational to our students. There is the talk, there is an article about Indian heritage, and then there is about career corner, job opportunities after physics honors, all the institutes that are there, AFR, Homi Bhabha Institute, IACS, etc. There is a list of all possible courses they can enter into, academic courses and so on. And then articles about expansion of the universe, Hubble's law, and what all is very famous these days, gravitational waves, and so on, matter, antimatter, annihilation, and so on. So these were the topics that they chose for this month's magazine, Comet Neowise, as you can see. And then there are further fun activities also. There are lectures on, there is a section on entropy, relativity, then virtuosity. All that you can see here has been done entirely by the students, and no help. So these are the paintings made by the students of our department ourselves. Some computer science students have also pitched in. So this is to develop the ambience of science and culture, and the culture of quest for knowledge. There are crossword puzzles also, and there are questions and so on, riddles, etc. So, and that's the team. And I just wanted to display it so that it is inspirational to the students to see that all the teachers are watching, that they have done hard work this month and shall continue for each month, as they have a complete team working on it. So that's it. Thank you so much for giving 2 minutes to me, Dr. Seema and Dr. Bindal. This is the work of our students.
Yeah. Thank you, Dr. Punita, for showcasing that. So
Thank you
now,
so much.
now we come to the valedictory session. So I begin formally. So respected Professor Ghatak, Professor Anurag Sharma, Professor Rajaram, and Professor Vijay Singh, who is right now present with us, and dear participants. I, Dr. Pushpa Bindal, welcome you all at the valedictory ceremony of the online national seminar, Exploring Physics with Experts, organized by Department of Physics, Kalindi College, and sponsored by Nasi Delhi chapter. This seminar was organized with the motive of giving young undergraduate university students a flavor of physics at its very best, from the very best in the field, so that they could get motivated and learn to enjoy it. Faculty to revise their basics coming from these eminent physicists. The participants have benefited a lot. It is evident from the comments and the feedback which has been received so far. In a way, these online seminars are a boon in disguise. It has given an opportunity to the students and faculty from different states to come together on these platforms without an actual travel and much expenditure involved. We had 242 registrations, out of which roughly 200 are students, and these are from different parts of India: Delhi, Bihar, Haryana, Himachal Pradesh, Jharkhand, Karnataka, Madhya Pradesh, Punjab, Rajasthan, Uttar Pradesh, Uttarakhand, West Bengal, Telangana, Odisha, Madhya Pradesh, Kerala, and Kolkata. And they have attended the national seminar via Zoom link and also the YouTube channel of Kalindi College and Nasi Delhi chapter. Huge participation by students and faculty signify the huge success of this seminar. Discussions that are followed by each talk, they are also really great. So I would take this opportunity to sincerely thank Professor Ghatak and Professor Anurag Sharma to have faith in our endeavors and sponsor the seminar. I extend my heartfelt thanks to all the resource persons. They have spared their precious time for this seminar. I extend my heartfelt thanks to also the Principal Madam, Dr. Anjula Bansal, for supporting all the initiatives of Physics Department. I thank the faculty members of my department who are also members of the organizing committee. Dr. Rachna Kumar, Dr. Punita Verma, Dr. Chiransa Srivastava, Dr. Rashmi Menon, Dr. Mazhar, Dr. Arvind, Mr. Ankur Anand, Dr. Savita Sharma, and Ms. Varsha. I am so thankful to all of them for devoting time in making all the arrangements along with taking their scheduled classes. So just as all good things come to an end, we have come to the end of this seminar. Now I request Dr. Seema Gupta to take over and formally close the session.
Thank you, Dr. Bindal. Thank you everyone for being the part of this national seminar. I'm sure that the students are the one most benefited by all these lectures, and also the faculty members. Simple concepts of physics explained in such a beautiful manner. That was the beauty of all these talks. I look forward to arrange more of such lectures in our college in future. Thank you everyone. So with this, we announce the formal closing of our national seminar.
Yeah, the feedback link is once again shared in the registered email IDs for all participants. So kindly fill that up so that we can process further.
Yes, it's necessary to